Now that we've figured out how to numerically do timed drains, let's look at a slightly different case. In this case, the tank has oil. Used to be pressurized. To reduce the draining time. The tank shown, which I'll draw shortly, is 6 meters tall. 2 meters in diameter. Oil is originally 5 meters deep. Density oil is 880 kilograms per cubic meter. Outlet port is 2 centimeters in diameter. Here's our tank. Here's my outlet port. So it's oil. Here's the original oil depth of 5 meters. Tank diameter is 2 meters. Total tank height is 6 meters. Outlet diameter is 0.02 meters. And the oil is going to come squirting out. And there's some pressure in the air up here. So we'll increase this pressure to force the oil out faster. The outlet velocity we'll assume is given by the following formula. 2g times the height of the oil plus twice the pressure divided by the density. Okay, so we increase pressure above 0 gauge and we get a little bit more exit velocity. So P is gauge pressure of air. So here, let me put a little pressure meter on here. Meter, 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 meter. There, gauge pressure. We'll assume that the temperature in the tank remains constant. So delta temp, therefore isothermal. And the air pressure is given by the following formula. So P is equal to P0 plus whatever the atmospheric pressure is times L minus H0 over L minus H minus pressure atmosphere, where L is the tank height. In this case, it'll be 6 meters. And H, as we've already said, is the elevation of the surface of the oil above the outlet. The initial pressure, so P initial is 300 kilopascals, and the atmospheric pressure, we use 100 kilopascals. Okay, so if we were to apply continuity just like before, we would come up with a drainage equation, and after quite a bit of algebra, we would come up with an equation that says the following: dH dt equals negative area of the exit, area of the tank, multiplied by the square root of 2GH plus 2P over rho oil. Now, it's not going to take too much to figure out that pressure is a function of depth in the oil. So this 2P, this P is not a constant. It changes as H changes. So doing an analytical analysis, good English there, trying to find an analytical solution to this is probably not impossible. Things that are in square root forms like that are findable. But now that we have another tool, we can just go ahead and do this numerically to predict oil depth at time. And let's just do it for 1 minute time intervals. So as this tank drains, what's my tank? There it is. Come back here, tank. You're welcome. Okay, so we pressurize this, open a valve, and this starts to drain. We're not adding additional air in here, so the pressure is going to go down as the tank drains. It's still above atmospheric, so it's not going to draw a suction and then stop draining. So we want to see how much oil we can get out of this tank over a 1 hour drainage interval. All right, well, how do we do that? Pretty much the same way that we just did the last problem. So let's go ahead and do some analysis. So we have dH dt equals minus AE over A tank, square root of 2G cap H, that's a variable, plus 2 over rho times P0 plus P atmosphere, L minus H0 over L minus H minus P atmosphere. And I'm having a hard time fitting that in. That's all there. H is unknown. Rest are constants. So, if you recall, our old update formula was that H at T plus delta T equals H at T plus delta T times dH dt. So that was our numerical approximation. And we'll just apply the same thing here. And in fact, the our tool we've just built can probably be manipulated with a subtle change into doing the work for us. So let's put in our known values. We know that H at T equals 0 equals 5 meters. That was given. We know that the exit area is 0.02 meters quantity squared over 4 times pi. We know that the tank is 2.0 meters quantity squared over 4 times pi. We will find out when we take the ratio of the areas that all that's left are the diameters. You know that P0 is equal to 300 dead pascals, 300 kilopascals, and P atmospheric equals 100 kilopascals. AE over AT happens to be equal to 0.02 squared over 2.0 squared, which is little d squared over big D squared. So that part of our prior program we can use. In fact, the only thing we really need to change, quite honestly, is the structure of the dHdt formula. So there's our dHdt formula. Let's go into our R script and modify our prior code. Alright, easiest thing to do is to make a new script. Go to the old one, copy everything, copy. In this case, it's a P-R-E-S-S-U-R-I-Z-E-D cylindrical tank by Euler's method. Here's what changes. Alright, so after I've made those changes, let's go examine what's new. We're going to need a pressure function because pressure is dependent on the depth and the depth is dependent on pressure. Our update function is changed. It basically affects the equation in the analysis. This is the ratio of areas times the square root of 2gh minus 2 over rho multiplied by whatever the pressure value is. The inputs, diameters, G, density of oil, initial pressure in the tank, atmospheric pressure outside. The differential pressure in this case is 200,000 pascals. Tank height, initial depth. Final depth was by trial and error, and we'll see that in a second. Let's go ahead and change this to like 2. Alpha we don't even need anymore. We need a pressure vector, a lapse time vector, an any vector. Initialize the any vector, initialize the pressure vector, and now we compute the updated time, the updated head, the updated pressure. Break when the head in the tank gets less than our stopping criteria, and if we exit the loop by maximum iterations, just report that. And then we're going to make 2 plots. So PAR MF row equals concatenation 2 1 means 2 rows, 1 column. We'll have seconds, depth in tank on one axis, time to depth, differential pressure, and I guess this label should be pascals. And that's pretty much our script. Okay, let's run it. First we'll clear this. Okay, save it. Run it. Our current stopping depth is 2.5 meters. Run. And it says it takes 1,600 seconds to get 2.5 meters, and the differential gas pressure is decreasing as expected. When it gets to 0, it just means the inside and outside are atmospheric. Drop that to about 1.6. Save, run it. It's almost 3,200 seconds, and our question was what will we get to in an hour, which is 3,600 seconds. Save it, run it. 33, 36 is pretty close. 49, save it, run it. 48. Save it, run it, and so somewhere between 1.48, 1.49 is the end depth. And that's how we can use our numerical method to simplify problem solving. That concludes this example.